Next up, we have Dr. Husseini from Riverlane.
Cool. Presentation mode. Right. Hi, everyone. My name is Andrea Husseini. I'm from Riverlane, which is a quantum error correction company based in Cambridge, United Kingdom. And today I'm here to give a two-part talk. Part one will be about the motivations behind a fast event distribution over a hardware parametric large-scale control system. And the second part will be given by my colleague Jan, where we'll dive a bit deeper into the implementation details and technical challenges that come with building such a system. So I will start a little bit with basically explaining this entire large title of the talk, breaking it down into the pieces and understanding the motivations of all of these elements. So why do we actually even need a hardware parametric large-scale control system, which is a real mouthful? When we look at qubits, qubits are inherently noisy, which means that we need to combine huge amounts of physical qubits in order to make logical qubits to then perform logical operations and scale towards useful quantum computing. That really informs this large-scale part of the system that we need to build. On top of that, each qubit technology is inherently different. I have some examples of qubit technologies here. It's not the complete list. We know there's a lot in the industry. But for each qubit technology, we see different advantages and different limitations. There's coherent times, timing requirements are different, the scaling challenges and limitations differ. So for that reason, we need something that I'm calling a parametric control system. Such a system would be able to not only adapt to different technologies, but could also develop as different architectures and qubit technologies arise and be able to adapt to such modifications and advances in the industry. And really, at the heart of all of this, of these large-scale fault-tolerant quantum systems, are control systems. They enable us to operate on qubits, but in order for us to build such efficient large-scale quantum computers, we really need control systems that are built with the different qubit types and their requirements in mind. And they need to be built such that we don't have to re-architect them from scratch every time the industry moves forward. So here I put a picture of the current iteration of Riverlane's control system, Delta Flow Control DC1. We spoke to a lot of labs and a lot of customers and did our own research into different qubit technologies. And from that, we extracted a bunch of requirements that we think are core to actually building a large-scale and future-proof control system. One of them is strict time determinism, and that is across the entire system, especially when we scale to systems that are across multiple physical modules. Then we have control over pulse parameters, and this is something that really differs across different qubit technologies. That could be things like phase, frequency, amplitude modulation, cross-channel alignment to picoseconds. And lastly, there's flexibility, and that's flexibility across many different channels. Programming, setup, scaling, all of that. But then why do we also need fast event distribution specifically? Why can't we just have a hardware parametric large-scale control system and be done with it? This comes down to the error correction cycle. So the error correction cycle is the cycle of operations. It starts with us operating on qubits, qubit control. We do some pulses on qubits. We already know that qubits are inherently noisy, so the operations aren't going to be perfect. We read out those qubits, read out those states, and we pass that readout data to a decoder. That decoder needs to process all that readout information in real time and pass feedback back to the control system in real time within coherence to make corrections on those qubits. And we need to be doing this loop about 1 million times per second to reach some sort of fault-tolerant, useful quantum computing. So for that, we also already know that we need something that operates fast. For this talk, I'm focusing on this middle part, just the control system requirements. But we know there's a lot more that comes into the decoding part of the system as well. And that's another part of what Riverlane really puts their efforts in. So on top of the requirements we saw before, we need to add this extra requirement, distributing data and communicating decisions in real time. This could be things like fast feedback, mid-circuit measurement, or branching. And when we consider these multi-module systems, multiple physical boxes, we need to be able to do such real-time operations across the entire system. no matter where these operations are going, which module the readout data is coming from, and where the signals needs to be operated on next. Another thing that we really need to take into consideration is the different applications, circuits, and algorithms that users want to run on their systems. And we can categorize them in terms of the feedback latency and also the time during which we need to get them to complete. So things in the lower left-hand corner, those are your within control flow, within coherence times operations, sub-microsecond, ultra-low latency. We also have things like circuit-level algorithms and some calibration routines that can maybe be a little bit slower. We can do it within calibration drift. The latency then pushes up to maybe about a millisecond. But all of these considerations and all of these levels of feedback need to be exposed in a singular control system for us to really move forward to fault tolerance. With all of that in mind, we're building something that we're now calling Delta Flow Control DC2, the next generation control system, which scales up to about 100 physical qubits. And we have three sort of pillars of this control system to satisfy all of the above, which I just talked about. One of them is that the control system has an inherently distributed architecture with parametrizable, purposeful built blocks. What that means is that the computation is distributed along the entire system and pushed to the periphery of the system so that it's as close to the outputs as possible, so we can do this fast feedback. And these purpose-built blocks allow us to be very efficient with what we're doing and targeting into different qubit technologies. Then we're also exposing different levels of computation to address the different latencies of different applications. So we have different interfaces and programming languages that are appropriate for such feedback levels. And lastly, we have dedicated links. And this is something that my colleague Jan will go into in a lot more detail, because the way we link multiple modules efficiently while maintaining fast feedback is really crucial to how we scale the entire system. And they're purpose-built to different applications and different latencies. So with these requirements in mind, we know that then DC2 addresses those two core parts of the title of the talk. It's a hardware-parametric system because we can configure the architecture of the system and put the blocks together based on the requirements of the underlying qubit technology. And it can operate at large scale across a lot of modules. And it enables fast event distribution across different levels of latency and different programming interfaces and languages. Now, my colleague Jan will dive deeper into technical details, so we could pause here for some questions about this part, and then I'll hand over to him to go into a bit more technical detail.
Yeah, let's thank Dr. Husseini. Open for questions.
We're also happy to do combined questions at the end for both parts, whatever's easier.
I have some questions, but maybe it makes sense to hear the second part then. Yeah. And if you want to come back up afterwards,
I'll stay here.
Sure, sounds great. We can proceed with the second part of the talk.
There's two parts to this. This is on your left side. Here. Yeah, it's going to be easier. And then this is your microphone.
All right. Hi, everyone. So I'm Jan Snoeijs. I'm an FPGA designer at Riverlane. And Andrea gave us a nice overview of the requirements for a control system to be compatible with error correction at scale. And I will now dive into a bit more of the architectural decisions and solutions we came up with during the design phase of our control system to address those requirements. So the first thing that I want to reiterate is that a large-scale control system is inherently distributed. And then this is because of the highly parallel nature of the interface between the control system and the quantum computer. And so it is important to distribute the compute across the stack and going down to the bottom, adding more and more parallel elements to fulfill that parallelism. So at the top level, we have a user node, user PC. This is used for orchestration, offline programming, or analysis, and system state management. Then at this middle layer, we introduce what we call real-time compute nodes. These are targeted at time-restricted operations at medium speed. So that would correspond to the category of within the calibration drift that Andrea mentioned earlier. And then finally at the bottom, we have those deterministic sequencers, which are microprocessor with a very small instruction set, but are very efficient at executing them, which means very low latency and absolute deterministic control. So then we map those different levels of compute to a physical architecture based off clusters. So in this example, we have 2 clusters in orange. Each cluster has a main device and up to 8 daughter devices. The daughter devices have the low-level drivers to connect to the quantum computer, and the main device is responsible for programming all the devices in the clusters and synchronization of operation within the cluster. Then we extend that principle to a multi-cluster structure where we introduce this supercluster, which has a cluster synchronization card to do synchronization between clusters. And then we have at the top again the user PC node where we expose our Python API and access to user C++ that will land onto the user CPU nodes. So the main devices are FPGA SoC devices, so field programmable arrays, and system on chip, which offers both programmable logic and hardcore CPUs onto which we map our real-time cores. And then we need various types of communication links to move data efficiently across the system. So the first type of link that we need is programming links to program the various memories on all of the devices, like instruction memories of the sequencers or pulse data memories. So between the user PC and the main devices, we have programming links on physical network links, and then for within the clusters, we have optical links. Then we introduce these purple links, which are used for fast event distribution. And so these are used to transfer process readout data from the daughter devices to centralized locations in the clusters, and then synchronize events back down to the daughter devices to resume synchronous operation after readout. So the reason why we have dedicated links for that is that this link is part of the error correction cycle, which requires extremely low latency, but doesn't move quite as much data as the programming links. So they have very different requirements, which makes sense to have a dedicated link for that. Next, we introduce the magenta links for clock distribution. So this is a daisy chain structure where each device recovers the reference clock from the previous device in the chain, based on an active clock recovery mechanism where we measure the phase difference between the reference clock and the recovered clock until we get alignment. And so this is a scheme demonstrated by a group at CERN, and they demonstrated latency under 25 picoseconds. So we believe that this is a more scalable approach than a passive clock synchronization scheme, which relies on cable length matching, which is harder to manage for a large-scale system. So now that I explained the architecture, the overview of the cluster architecture, I want to dive a bit more in the contents of the daughter device. So we package up components in atomic control units, which are so ACUs for short, in which each ACU has a sequencer and a set of peripherals. So typically signal generators or readout modules. These are really to interfacing to one or a set of channels to the quantum computer. And then on top of that, we have the local event distribution unit, which is used to propagate events up the chain of in further clusters. And so we really want some flexibility at this level, because each channel, depending on the type of qubit or even within the same QPU, might have very different requirements. So we want those signal generators to be highly configurable, and maybe we want to add more signal generators in to do multi-tone signal generation, or change some parameters in these blocks. So we have developed an internal tool to automate and configure those ACUs as we want. And so I wanted to show an example of that, of a parameter that we might want to configure on these RF generators. And so the idea is we want to generate a sinusoidal pulse and modulate it with an amplitude profile. So this is a fairly standard amplitude profile. So depending on the type of channel that we are talking about, we may there may be a lot of variance in the length of those pulses. So in superconducting, typically the pulses have ranges of few tens of nanoseconds, but for AMO, these pulses might go up to the millisecond. So this represents a memory footprint challenge if we want to store that profile in memory. So these longer pulses are good candidates for compression. And so compression scheme we use is cubic splines. So we fit this curve to a set of cubic polynomials. And then we store parameters that can be derived from coefficients of these cubic spline polynomials. And depending on the number of splines used to fit this curve, this yields up to between 10x and 2x compression ratio over storing the entire pulse in memory. And so the way that we implement this in the hardware is we store these cubic splines into a memory, and then we pass these cubic splines to a pulse shaper unit, whose job is to decompress this in real time, such that its output is basically a very good approximation of the initial amplitude profile, which we then mix with the pure sinusoidal wave coming from the numerically controlled oscillator, and then the signal is then sent to the DAC, where it becomes an RF pulse. And so here, really, like the feature that we want to be configurable is we want to be able to bypass this pulse shaper for channels that don't need compression, so playing short pulses, and changing the data format of how we want to store the samples into that memory. So in this case, we'd store raw samples, and they would directly be multiplied with the NCO output. I also want to mention that there's a paper coming out soon on more advanced techniques that we developed around pulse compression. So yeah, one more thing. I wanted to advertise for our open source experiment management platform, which launches this week. So we are organizing a workshop around that on Wednesday at 10:30 in Theater 1. Thank you very much.
All right, so we'll take questions for the previous two talks now, so we have a fair bit of time. If you have a question, if you could just come up to the mic, that would be appreciated.
Good job.
My name is David. Nice talk, thank you very much. I saw that you're using the RF SoCs as one part of your chain there. How is your work different from the open source firmware that is called KIC?
Do you want to?
I think there's obviously a lot of value in developing and delivering open source platforms. What we really try to do is also provide a stack that is fully verified and tested at all levels and integrated with our other solutions. So while this is the next generation control system, we're actually working towards a QEC stack, a quantum error correction stack, where we integrate control fabric and a decoder in real time. So we see that our work in control is really a stepping stone to that bigger goal, where maybe we then use that as an opportunity to differentiate ourselves in a slightly different direction.
All right, thank you.
Yes, I was wondering what's the difference between hardware parametric and qubit agnostic?
Yeah, I think that's a good question. They're quite close terms. I think qubit agnostic is really being able to drive different qubit platforms from the same control system, which that doesn't work entirely like that. With clearly the low-level electronics, analog electronic needs to be very tuned to the QPU, to the specific QPU. By hardware parametric, we also mean parameters that may change for different channels, like in superconducting qubits with tunable transpond architectures. We have different types of lines that we need to drive, and those lines have very different requirements. So we might want to change parameters for signal generators depending on that.
Thank you.
curious on the interface of two locations. One is the event you're distributing. What kind of topology between the different between your master FPGA and the different daughter board, and eventually how they are going to scale up. That's one thing. The other is also between the, looks like your daughter card also have FPGA. I assume that's a different FPGA. What kind of interconnection between them? What kind of bandwidth limitation?
Yeah, so that comes back between to the different types of links that we introduce in our architecture. So so within one cluster, so the daughter devices are also FPGA devices. So currently we use RFSoC devices, so these programming links are optical links via transceivers. So optical transceivers. So these are high bandwidth links to move data, but these links don't guarantee determinism. So they are used to program the boards before an experiment and collect data after an experiment. Whereas the other one, the event distribution links, so they are really links to that provide determinism, where we only send processed readout data back to the main device from the daughter devices via just a direct cabling, and then the main device has another link. So there's basically one link for upstream, one link for downstream, to send synchronized events back to the sequencers on the daughter devices.
So if something kind of mid-circuit merriment, then you need to, that also goes through that event link.
Yes, exactly. So the idea is for fast feedback, we only want to go through that event distribution link. So the idea is we process the readout data very locally on these daughter devices. The output is processed readout data, so zeros or ones, really low amount of data locally. And then the event is propagated up the chain of event distribution units and back down again. So, and then every time we need to switch to another device via this link, we pay a price in latency, which is about 100 nanoseconds.
The event link is just a GPIO kind of star structure.
Yes, it's a star structure. Yeah.
Thank you. Simple question. Your daughter cards use mixers and local oscillators, or they use direct RF?
So we use digital mixers. So it's all direct RF, and the RF SOC platforms allows for generation of up to 10 gigahertz signals with direct RF.
If anyone has questions later, we also have a booth, so we'll be there and we can talk more about anything that's interesting.
I have one question. The temporal resolution of your like the amplitude envelope, what is that?
So that is something we can configure. Currently we are targeting 2 gigahertz as a maximum, which is quite necessary for multiplex readout, to generate pulses for multiplex readouts when the qubits are quite spaced far away in frequency. We need high bandwidth there, but we can tune it down for pulses that are longer and don't require that kind of resolution.
Awesome, thank you. One more question.
Hi, can you say something more about this Aqueduct platform? What does it do?
Yeah, so this is a open source software that sits kind of on top of the control stack, and it's used for data management, scheduling, sort of your offline things. And yeah, there's going to be a whole workshop with a demo and a hands-on kind of opportunity to try it out.
Is this open source?
Yes, yes, fully open source.
Thank you.
All right, let's thank the speakers again.